start the recording. And that's how I do my class and upload to the YouTube. So as announced before, October 23, yes? 안 들려요? 들려요? Better? Is it better? Can you hear me? Or still my own voice? My own voice. Okay, so I'll try to speak loud until my students correct the setting. October 23 next week, right? Next Wednesday. Oh?
채널을 손대지 말래. 요거
Actually, it is working, but it doesn't. Now, it sounds better. Doesn't work. Okay, I'll speak as loud as possible, and if you still have trouble understanding me, raise your hand. Okay. So October 23, Wednesday, we have quiz number 2. And that's a 2.5 hour quiz, I think. So 14 to 16:30. And I guess maybe you need more time. So I'll try to set the problem for 2.5 hours, but depending on the case, it may take longer. And actually, you have seen the cases. If I ask you to check the Cauchy-Riemann condition for tangent z, it will take quite a long time, right? So you can prepare 3 pages. cheating sheet. Actually 2.5 pages, but I will allow you to have 3 pages. And last week I made a mistake. So I found that when you secant to z is secant to z tangent to z, right? So the previous note I made a mistake. So I hope you make a correction this time. And I don't know, somehow I feel a bit warm, so I'll just take off my jacket. So one of the potential candidates for the next quiz is like check for Cauchy-Riemann of CSCZ. That would be nice, right? And second type of Z. CSCHZ. And depending on my mood, that would be a nightmare, right? I think the first 1, 2, 3 maybe can be handled in maybe half an hour, but tangent to z will take at least 1 hour, right? So you have to. So what would be the remedy? Okay, what would be the solution if I ask you to check the Cauchy-Riemann condition and find the derivative? So that is definitely one problem set for next quiz, and those are the candidate. And you have seen that I also made a mistake in the calculation, right? So it is very easy to make a mistake, especially when you differentiate the denominator with a complex form of functions. So what you can do is practice. So practice make it perfect. So I'm going to ask one of those 5 functions to check the Cauchy-Riemann condition and find the derivative. So I hope you do practice enough at home. So at least you can get the score for that. Sometimes we have a function, also composite function. So what is CR form for the composite function? That's one possibility, right? For example, we have ln z is r plus I theta, right? Of course, plus minus e to n pi. So logarithmic function is represented by r and theta. In some cases, we have r and theta representation. Then it might be, is my voice loud enough, or you can hear me? So how do we find the composite function? So we need to find out what partial x, partial u, r x, y, theta x, y. So actually you have learned the chain rule. So let's check. Delta u theta x, y would be u r x plus delta x y theta x plus delta x y minus u r x y theta x y, right? So let's say r x plus delta x y as r x y plus delta r theta x plus delta x plus y. We wrote this as theta x plus y plus delta theta. Then we can add a few zeros. For example, r. So this is r x y plus delta r theta x y plus delta theta minus u r x y theta x y. And then we can add 0 without changing anything. So I can do this xy plus delta r theta x plus y delta theta minus u x r x y. Sorry. U r x y theta x y plus delta theta And then you add the same thing, u r xy theta xy plus delta theta minus the original term rxy theta xy, right? So I haven't changed anything. You just subtract this and add the same thing, right? Then what you can do is you can divide this whole thing by first thing by delta r. So u r plus delta r theta minus theta plus theta plus delta theta minus u r theta plus delta theta and times delta r. Then it doesn't change anything, right? And then divide by delta theta u r theta plus delta theta minus u r theta and then delta theta. Then it's the same expression, right? So some of you still need some time to copy, I guess. So then partial x partial u is actually delta x goes to 0, delta x over delta u is when delta x goes to 0, we have delta theta goes to 0, delta r goes to 0, right? So delta x goes to 0 means delta theta and delta r goes to 0 at the same time. So if you happen to remember the form, then we have delta r, u, r plus delta r, theta plus delta theta, over delta x delta r, plus delta theta, u, r theta plus delta theta, minus u, r theta. So you can write down as a delta r, delta u, delta x, delta r, plus delta theta, delta u, delta x, delta theta. So actually you probably have learned in your freshman years as a chain rule when you learn partial derivative. So partial x, partial u is partial r, partial u, partial x, partial r, plus partial theta, partial u, partial x, partial theta. And then you can apply the same thing for y. So likewise, partial y, partial v can be written as partial r, partial v, partial x, partial r, plus partial y, partial theta, partial v, partial y, partial theta. So we still need to find out partial x, partial r, partial y, partial r, partial x, partial theta, partial y, partial theta, right? So let's do that in the next page. So actually I'm doing this for someone you haven't taken a calculus class in high school or the freshman calculus in another department. So that can be a good review for how to derive the chain rule for the partial derivatives. So this is the chain rule. can I move on? So this is your coordinate x, y. This is a point z, x, y. This is theta, this is r. So r is actually x squared plus y squared 1/2. Theta is a tangent inverse y over x. So partial x, partial r is easy, right? Partial x, partial x squared plus y squared 1/2. And so you can apply the chain rule, right? So you can set g as x squared plus y squared. Then you can put dz, dc, partial x, partial z. So that is 1/2 square root of g and 2x, right? So this is r over x over cosine theta. Because x is r cosine theta, y is r sine theta. So likewise, partial y, partial r is same. Y over r, sine theta. The derivative of theta is a bit tricky. So let's say h is tangent inverse t, then t is tangent to h. So dh dt is what? 1 plus h squared. A tangent to square h, right? So that is 1 plus t squared. So t dh is inverse 1 plus t squared, right? So d tangent inverse t is 1 plus t squared. It's convenient if you know this relationship. So let's go ahead. Maybe I'm going a little bit fast, or you know everything, right? Because you have learned how to make a derivative of an inverse function in your freshman years already, right? So, but I'm just reviewing for your benefit. So, partial x, partial theta, partial x, partial tangent inverse y over x. So we can say t is y over x. Then this is d tangent inverse t, partial x, partial t, right? So 1 plus t squared, and this is minus y over x squared. And t is actually 1 plus y over x squared times minus y over x squared. So that is x squared plus y squared times minus y is 1 over r times minus sine theta over r. Partial y is easier. Partial y, partial theta is actually 1 plus y over x squared times 1 over x. So that is r over cosine theta is r over cosine theta. So partial x, partial theta is minus r over sine theta. Partial y, partial theta is cosine theta over r. I think I probably should slow down. Am I going too fast? Or about okay? Okay, let's just be frank. Anybody who never had an experience of differentiating inverse tangent, raise your hand. If it is the first time, raise your hand. So everybody knows how to do that, right? Because I'm just reviewing the subject. Good. So I keep forgetting. So partial x, partial u is partial r, partial u, partial x, partial r plus partial theta, partial u, partial x, partial theta. And partial r, partial x is cosine theta. Partial theta, partial u is minus r over sine theta, right? So cosine theta, partial r, partial u, minus 1 over r, partial theta, partial u, sine theta. Partial y, partial v is partial r, partial v, partial y, partial r, plus partial theta, partial v, partial theta, partial y. So that is sine theta, partial r, partial v, plus 1 over r, sine theta, partial v. And one of the condition for the Cauchy-Riemann condition is these two quantities are the same, right? So CR condition says partial x, partial u is the same as partial y, partial v. So that means cosine theta, partial r, partial v, minus 1 over r, sine theta, partial u is same as sine theta, partial r, partial v, plus 1 over r. This must be cosine theta, partial v. So cosine theta, this is u, partial r, partial u, minus 1 over r, partial theta, partial v, minus sine theta, partial r, partial v, plus 1 over r, partial theta, partial u is equal to 0. For all theta. So what is the condition for A and B such that A cosine theta plus B sine theta is 0 for all theta? Equal to? Both are 0, right? A and B are 0, right? So from this condition we have partial r, partial u is 1 over r, partial theta partial v, partial r partial v is minus 1 over r partial theta partial u. So that's the Cauchy-Riemann condition for polar coordinate. And actually you obtain the same equation for the other condition. So I will give as homework. So homework. So this is another homework. So you can check that. The same condition arrives. So Cauchy-Riemann condition for the polar coordinate is the following. It's partial r partial u is partial So that's about find the derivative in the complex functions. Actually, the most important topic for this semester is complex integration. And this is the sole purpose of learning complex analysis, to do the complicated integrals. Let's start with a very simple theorem. T is the domain, complex numbers. And assuming we have a closed curve called C, and D. If so let's say f is an analytic function inside of C. So analytic function means differentiable. And finite. Then this is Cauchy's integral theorem. This is very simple statement. If fz is differentiable inside of closed curve C, then this integral is 0. And this is actually a very powerful theorem, and you're going to learn why it is later. So let's start with this, fz, u xy plus I free xy. Z is x plus iy. Tz is tx plus ity. Then u plus free tx plus ity is simply u dx minus free dy plus I free dx plus u dy, right? So let's try to evaluate this integral and see what happens. So u free u. So let's try to do this. C fz tc is actually cross C. U dx minus free dy plus I C free dx plus u dy. Let me check. Probably you remember this integral, fx dx plus fy dy. Remember this form? So this is actually f dl, right? So you can convert this into two-dimensional integral, partial x partial fy minus partial y partial fx dx dy, right? Remember that? Stokes theorem? So the first integral, u dx minus free dy, is actually, so this is fx, this is fy, same as s minus partial x partial free minus partial y partial u dx dy, right? And what about this? This is, what is partial x partial v? Minus partial y partial u, right? So this is 0 by CL. So this is 0, right? The other one, v dx plus u dy is again as partial x partial u minus partial y partial v dx dy. This is again 0 by CR, right? So we have a very simple proof that so still CR and finite inside of C, then C equal to 0, right? So before I proceed, maybe we can take a break, a few minutes, and I will let you know how. What was the latest number for the YouTube class? Is it 5 or 6? 5? So I can change this. So this is break, so I can do this. So this is your domain. Okay, what about FC is 1 over Z? So analytic means both satisfy CR condition and finite. 1 over Z, this satisfies CR condition, right? But can you say it's finite at the origin? No, right? So this function is not analytic at Z equal to 0. So if you do this integral, we are not sure whether this is 0 or not. So this integral cannot be determined by Cauchy's integral theorem, so you have to do it by hand. So we can say on C, Z is R exponential I theta, right? On this point, or dz is R exponential I theta, I d theta. So this integral can be changed into the polar integral as 0 to 2 pi R exponential I theta, r exponential I theta, I d theta. So luckily these factors will cancel each other. I 2 pi I. So this integral is 2 pi I. If we do this integral, or so we can extend this into the z to the power of m. So I will let you copy if you haven't finished. So we can continue, you can expand this so this is a unit circle, this is your circle. How about this? Z to the m dz, like so. So m is integer. So z on c on this circle r exponential I theta. C to the m is r to the m exponential I m theta. dz r exponential I theta I d theta. So this closed integral can be converted into the polar integral 0 to 2 pi r to the m exponential I m theta r to the exponential I theta I d theta. So r to the m minus 1 over I is 2 pi minus I m minus 1 theta d theta cosine m minus 1 theta minus I sine m minus theta d theta. What about this integral? So in general, as m is integer, usually 0, right? But when m is equal to 1, what happens? Cosine 0 is 1. So this value is 2 pi over 0. Right? On the other hand, this is always 0. So this integral is actually 2 pi I 1 0. M is equal to 1 otherwise. So this is a very interesting result, right? Okay. What about the point is not at the origin? Somewhere ahead. You still need time to. How about we have some point? unit circle. This is C. So what about this? So instead of a center, we have some other point, not the origin. Then any point on Z can be on C. Z can be written as R Z naught plus R exponential I theta, right? Or same as before, dz is R exponential I theta I d theta. So this integral is same as this, 0 to 2 pi R to the m exponential I m theta R exponential I theta I d theta. So same as the case of the origin. So result will be 2 pi I or 0 otherwise. So this is true for circle. So above result is true for the circle of radius R, centered at z equals c naught. But what if it is not a circle? Question. C is not a circle. That would be an interesting case, right? So if it is not a circle, then what do we do? It's a general curve. General curve. So what we do is actually we change into the following. Assuming that this is the same, not quite same, but let's try to make it similar. Oh, perhaps I can copy. I'll try it again. Great. How about that? Okay, so in the same page it works. Okay, so I will make a little bit of detour. Oh. So let's say this is C1, C2, C0, C3. So if you use a magnifier, this is a magnifier, then this part will be more like C2, C3, right? This is epsilon. So C prime is C1 plus C2 plus C rho plus C3, right? So what happens? This is C prime. For the C prime, outside, right? So as long as this curve is concerned, this point is outside, right? So this integral will be 0 by Cauchy's integral theorem. C prime so C prime is this closed curve with the C1, C2, C0, C3, and coming back. So for this curve, this point is outside, right? So we can apply Cauchy's integral theorem. We know that this is 0. But if this C2 and C3 are opposite, so we can see that as as epsilon goes to 0, this is C2 C3 is 0, right? Because C1 and C2 and C3 are in the opposite direction. So if epsilon is going to 0 and they are closing to each other, then this integral will cancel each other. They cancel each other. And also, if epsilon is going to 0, then C1 becomes C, right? As epsilon goes to 0, C1 becomes C. So we have a very interesting result. So maybe I'll write down here. This Z becomes C zero, which is opposite direction, is 0. And clockwise 0 is actually minus of, if we change the direction to counterclockwise, 0, dz. So we have this C is actually 0, right? And then the result is the same as 2 pi I m equal 1, 0 otherwise. So actually it doesn't depend on the shape of the curve. So any kind of curve will have the same result. So I put everything in one page. So you have to read carefully. But conclusion is, it doesn't matter whether it's a circle or just an arbitrary curve, we have the very good result. So this is a really important result. So can I move on? So for arbitrary closed curve C, we have otherwise if Z is inside of C. And we actually obtained this result from the Cauchy integral theorem. Then this tells this property has a lot of important results. For example, if C can be expanded by the series, it's called the Laurent series. Then what happens if we integrate this function? So this function can be very complicated, a lot of information. So this function can be specified, all different coefficients, Pm minus 1, blah, 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 B1, A0, A1, A2, many, maybe infinite order. But if we integrate this, what happens? All the coefficients doesn't contribute, only these terms survives, right? So 2 pi I P1. So this one has a special name called the residue. So this B1 is called the residue. And so complex integration of FC needs transformation of B1. So no matter how the function is complicated, you only need to find B1 to evaluate the complex function. This is called residue. So how do you find B1? That's the question, right? Now we need to know so let's go back to some history. So complex integration. The history of complex integration is actually from the war game. So usually the big progress in science or math was motivated by the warfare, and it was 1879, July 14. So anybody remembers what happens in that particular date? 1789, July 14. French Revolution, Bastille Day. So the Napoleon actually hold the power, and then the Europe is in war. So this is France, and this is England, London. So Napoleon wanted to conquer London, but the British has the strongest navy at the time. So Napoleon was trying to invade England by attack London. But the London is kind of natural fortress, naval fortress, because the tide is very high. 조석 간만의 차가 very high. So if you want to attack London, then you have to analyze. So when would be the lowest tide? So Napoleon asked Cauchy to calculate the tidal force. And the origin of the tidal force was well known by the time, right? Because the gravitational attraction between Earth and Moon. So this is Earth. This is Moon. So you need to. This is R1. This is R2. And so this is R1 minus R2, right? So gravitational force is tidal force is proportional to R12 square, right? R1 square plus R2 square minus 2R1 R2 cosine theta. And so Cauchy ended up with the necessity to, but because he has to take average of the whole Earth surface, so Cauchy needed to the following integration. That is 0 to 2 pi a plus b cosine theta over this theta, right? So because A is larger than B, so Cauchy needs to find this integral. But about 1785 was 200 years ago, right? And these days, this integral is very easily done. You can use mathematical MATLAB or Fortran or Python or maybe C++, you can just numerically integrate, and then you can predict when would be the optimum date to the attack. But Cauchy doesn't have a computer, of course, right? The best weapon he had was pencil and paper. So he has to do that using by hand. So what he did was so let's say Cauchy needs to calculate this function a to b cosine theta over d theta. So he tried to use a complex integral. So cosine theta was z plus 1 over z, right? So z is exponential I theta if unit circle. dz is exponential I theta I d theta equals z I d theta, or d theta is I z over dz. So Cauchy found that if you can transform this integral into the following form, I over 1 unit circle a plus b over z plus 1 over z times z dz. C is a unit circle. That's what he did, actually. So this is 2a plus b, c plus 1 over z, z over 2d, dz, right? Two over I, c. What happens? 2az plus bz square plus b over dz. So we can say ib over 2 z square plus 2a over b plus 1, right? Over dz. So we can c plus c1, c plus c2. So z1, z2 minus a over b plus minus a over b square minus 1, right? So we can say since if you assume a is larger than b, then we have 2 points here. This one is minus a over b minus b over a square minus 1. Say this is c1, and this point is c2. Is minus b over a plus so we know that if you have a partial fraction of this integral, then only one term contributes, right? Where is the other one? I didn't turn it on. So somehow this lecture will be voiceless for how long? Maybe half an hour until now. Sorry, I forgot. Actually, I think I turned it on, but so it's like watching 무성 영화 for maybe half an hour. So maybe I will explain it again. So let's do this. So remember the formula 2 over IB. We have C2 C2, right? So how do you find A1? For A, for the A, you multiply by Z minus C1 everywhere and set Z equals Z1. What happens? So this is C1 minus C2 is equal to A plus Z minus C2 over Z minus C1 B, and Z equal to Z1 equal to A. So A is actually 1 over Z1 minus Z2. B is minus A, right? Or B, we apply Z minus Z2 everywhere and then see what happens. So and set Z equal to Z2. B is Z2 minus C1 over 1. So this Z minus C1, Z minus C2 is equal to 1 over Z1 minus C2 and Z minus C1 minus Z minus C2, right? We can check. Multiply by together, Z minus C2 minus this way. So Z1 was minus A over B minus square root of A over B square minus 1. C2 was minus A over B plus A over B square minus 1. So C1 minus C2 is nothing but minus over A over B square minus 1, right? So our integral is the following. So our integral is the following. Oh, so we need C1. Oh, right. So we have a factor of 2 missing here, right? This is 2. So this A plus B cosine theta over this theta is 2 over IB. Z1 over Z2 is This is C, right? But this one is out. This one is 0. And this one, you know the result, right? 2 pi G2, 2 pi I. And Z1 minus Z2 was minus square root of A over B square minus 1. So IB2 minus root A over B square minus 1 times minus 2 pi I. So minus cancels each other. So B over 4 root A over B square minus 1 pi 4 pi A square minus B square. I think I have something wrong with 2. Let me check with my previous note if I have. Is it for pi? Two pi. So where was 2? Plus minus. We have vector 2 here. 2. So this is 2 pi over A square minus B square. Amazing, isn't it? So actually, Cauchy was able to calculate this, the optimum date for the invasion. So French Navy was prepared because all the scientific results, so they know which date has the lowest tide to attack Britain. So the French Navy after actually attacked London, but didn't succeed because of one person, the English Admiral Nelson. So even though the French had knowledge about the tidal force and then all the scientific data about the English Channel, but Nelson is better prepared for as a general. So even though the course is a tremendous effort to develop a science, the French lost the naval war. So there's some history about why we are learning this. But that's amazing because the Cauchy's integral theorem actually allows to do very complicated integral. And we are going to see the more of those results. Maybe take a break a few minutes before continue. 이런 So finding residue is really important, right? So we found that the complex integral can be found by just finding B1, which is residue. So the first condition you have to check is whether FC satisfies CR at everywhere. And check if FC is finite at Z0, then FC is analytic. If not, Z0 is called singularity or pole. Singularity or pole. So when Z is finite and CR, then it is analytic. If infinite and then it is simple pole of order 1 or simple pole. For example, C minus 1. Then infinite, right? But one, which is finite, right? So in this case, it's called simple pole or pole of order 1. And for pole of order 1, B1 is very easily calculated. Then residue P1 is called the residue. And if but to the M FC, in this case is called pole of order M. And in this case, P1 residue F Z naught is the residue is calculated by using this formula. This is easy to actually is easy to prove. So as long as the integral is concerned, we only need P1. We don't need any other information. So let's go back to the original Laurent series. Can I move on? So obviously, Pm plus Pm minus 1 plus Z minus C0 M minus 1 P1 plus A0 Z minus C to the M So what happens if we integrate m minus 1 times So if we differentiate by m minus 1 times, all the other terms will be 0, right? This is the first term which is not 0. So this is m minus 1 factorial b1, right? Plus other terms m minus 1 factorial a0 z minus c0 plus blah 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 blah. So if we set z equal to z0, what happens? This term all goes to 0, right? So that goes to 0. So m minus 1 factorial p1. So p1 is actually 1 minus 1 factorial m minus 1 factorial z minus z0 to the m fz, and you put z equal to z naught. So for example, how about fz is 1 over sine z? We know that when z goes to 0, fz is sine 0 is 0, so it's infinite. So if check if cfc z is this one. You need to have a L'Hopital's rule. That is then remember this rule? This is called L'Hopital's rule. But it was never proved. You just asked to remember that, right? So it's actually proof is very easy. You just do nothing. So check. Same as this. Delta goes to 0. Right? And then you subtract 0. fx0 plus delta minus fx0. 3x0 plus delta minus 3x0. Same, right? and then you divide by the same thing. Then nicely you can show that f prime x0, g prime x0. So z goes to 0. Sine z over z is actually 1 over cosine z 1. So sine fz 1 over sine z has a simple pole. Actually, simple poles and many points. Has simple poles at z equals 0, plus minus pi, plus minus 2 pi, many points. Another interesting function is I'm going to stop soon because I don't want to give you too much material to cover for next quiz. So maybe after one more example, if you don't mind. If you want, we can continue. Of course. Another interesting example is fc exponential z plus 1. When z is pi I, what happens? Exponential pi I is minus 1, right? So f pi I is infinite. So on the other hand, z minus pi I over exponential z plus 1, we can apply the L'Hopital's rule. Minus 1, just p1. And so after next week, we will cover some complicated integrals, but probably maybe we can just stop here today. So you can prepare comfortably for the next quiz. Right? So I think the first quiz covered everything about vector, right? So you don't have to worry about vector. So second quiz will be focused on complex analysis. So Cauchy-Riemann derivative, and what else? Cauchy's integral theorem, and finding residue. So those are the main focus for the next quiz. And I'm going to give you plenty of time, 2.5 hours. So it looks like some complex differentiation for CR will be important, right? Yeah. 어디? I will post on the website. No.
계산 또 지독하신 거 받으실 거예요?
한전 듣지?
작년 말이야?
작년에 계산이 지독했나?
네. 죽을 뻔했어요.